So problem 1. There are 2026 integers greater than 1 written on a blackboard, not necessarily different. In the move, Confucius chooses two integers, m and n, from different places on the blackboard, and replaces them with the GCD and the LCM over the GCD, okay? And he keeps moving while it's possible to do so. Okay? Prove that. Okay, so we have two things to prove. That regardless of the choices of Confucius, after finitely many moves, exactly one integer is greater than 1. Okay, so exactly one integer. So we have 2026 integers written on the board, and at two moves, we take two integers and we write two new integers on the board. Okay, and after finitely many moves, we should have exactly one integer greater than 1. Well, all the numbers written on the blackboard are positive integers. So if the number of integers is constant and exactly one of the integers is greater than 1, that means that the rest of them have to be equal to 1. Okay, so regardless of which 2026 integers we have written on the blackboard, we should, regardless of which numbers Confucius picks, we have to end up with one integer bigger than 1 and everything else 1. So we have to end up with 2025 ones, essentially. Okay. Okay. And prove that the value of m does not depend on the choices of Confucius. Okay. Right, okay. So a good place to start is, okay, so if we have integers mn, then, and let's say that GCD is g. So we can write m as GA and n as GB. And we know that A and B are coprime. And the lowest well, if the GCD is G, the highest common multiple is going to be GAB. Yeah, so if you take two examples, say 6 and 4, we have 6 is 2 times 3, and 4 is 2 times 2. So our LCM is going to be 2 times 2 times 3, which is 12. So, okay, so the LCM over the GCD, that's just the product of the two numbers. That's nothing special. So we have LCM of MN is GAB, and the GCD of MN is G. So the LCM of MN over the GCD of MN is AB. Okay, so it's not the product, fine. So it's not M times N, it's AB, fine. So prove that regardless of his choices, we have to get 1. Okay. Okay, so if we have GA and GB, these two numbers go to G and AB. Fine. So the product of the numbers goes down, right? Before we have product of the numbers is G squared AB, and that product goes to GAB. So we're dividing the product by an integer. We're dividing the product by an integer. So the product should decrease every time, unless G equals 1. Okay, so if G is 1, then that means M and N are coprime. So if G is 1, we go from AB to 1 and AB, which is good. So if Confucius chooses two numbers which aren't coprime, he decreases the product of all the integers on the board. And if he chooses two integers that are coprime, then we get a 1, which is what we want. Okay. Okay. Okay, the number 2026 shouldn't be relevant to the problem at all. Like the problem should be true regardless of the number of numbers on the board. They've just picked 2026 because that's the year of the paper. So let's try doing this with arbitrary numbers. Let's say we have 6, 4, 10, 15. And let's see what happens. So let's say, okay, 6 and 4 goes to, well, the GCD is G, so 2. And A and B are 3 and 2. So AB is going to be 6. We get 2, 6, 10, 15. Okay, and let's note how the product is changing as well, because that seems quite a natural thing to look at. So product before is 6 times 4 times 10 times 15, which is 24 times 10 times 15, which is 12 times 10 times 30, which is 360 times 10, which is 3600. So our product was 3600, and now that's gone to 2 times 6 times 10 times 15, which is 30 times 6 times 10, which is 180 times 10, which is 1800. So the product divides by 2. Okay. Now if I were to pick 10 and 15, we'd get 2, 6. The GCD is 5, and we'd get 2 times 3, so we'd get 6. Okay. Well, now 5 and 6 are coprime. So if I were to pick 5 and 6, we'd get 1 and 30. And there's no okay, so the product divides by G. So it divides um by the GCD of 10 and 15. So it divides by 5. So 1800 divided by 5 is 3 6 0 360. Yeah, 360. Okay. And then on the next move our product doesn't change, and we have a 1. So on our next move we're going to have, let's say we pick 2 and 30. Our GCD is going to be, so we're going to have 6, 1. Our GCD is going to be 2. A is going to be 1. And B is going to be 15. So we're going to have 15. And our product divides by GCD, so it's going to go to 180. Then if we pick 6 and 15, our GCD is going to be 3. 6 is 3 times 2. And for 15, we're going to have 3 times 5. So we're going to have 1, 2, 2. No, our GCD is 3. So 1, 2, 3. And then 2 times 5, so 10. I think this is probably, I guess if you're a viewer, this is probably quite a boring thing to watch, someone just trying examples, doing something like this. But I think this is quite an important part of solving a problem, just trying some examples and seeing what's going on. So I think this thing we have in the product is quite good. Um, yeah. So we divide the product by GCD, so we're gonna have 60. And then 2 and 3 are coprime, so we're gonna have 60, 1, 1, 6, 10. And then we're going to have 6 and 10. So we're going to have 1, 1, 2, 15 with product 30. And then we're going to have 1, 1, 1, 30. Okay. Okay. So, yeah, I feel like it shouldn't be that hard to show part A. I don't think part A should be that difficult to show because the product of the numbers. Okay, so let's go back to what we had at the start. So we have M and N. M is GA, N is GB. Product is G squared AB. And GA and GB, as we said earlier, goes to G and AB. So the product goes from G squared AB to GAB. Okay, so let's say our K numbers on the board are A1, A2, AK. Let's look at their product. So their product P is A1, A2, AK. And we have that each move, either that product is going to decrease, either that product decreases, or the GTD is 1. And to the only way we add 1 to the blackboard is from two coprime numbers. Yeah, okay. I feel like, yeah, this is not that easy. Okay, so the product is going to decrease. Okay, let's think about our example. So we had 6, 4, 10, 15, and we ended up with 30. 1, 1, 1. Why did we end up with 30? Well, 30 is the product of all the primes dividing all the terms of the thing. So it's okay, so we write it as our final number here was rad of 6, 4, 10, 15, which is I don't know if this is how you write it, but it's like oh 6 times 4 times 10 times 15, whatever. So it's the product of the primes dividing. So we have 2 divides this product, 3 divides the product, and 5 divides it. And 30 is 2 times 3 times 5. Okay. Okay, does this hold for other examples? Let's try with just 6, 4, 10, and 3 numbers. And let's see if we still get 30. Yeah. So if I take 6 and 4, we're gonna get 3. The GCD is 2, and we're gonna get 2, 6, 10. And then if we take 2 and 10, we're going to get GCD is 2. So we're gonna have 6, and the GCD is 2, and then we're gonna have 1 times 5, so 5. And then if we look at 2 and 3, we're going to end up with the GCD is 2, 3, 5, and then yeah, okay. So I think we have okay. I think there's a reason for this. So suppose a prime divides the product. Suppose the prime divides the product. If it's the if it only divides one term in the product, there's no way you can eliminate that prime from the product. Because to eliminate it from the product, you're going to need because the product every time you divide by g, and if the prime only divides one term in the product, the prime is never going to divide the GCD of that term and another term. Okay, yeah, I feel like yeah. So the answer should be this number. Like you can't decrease the product further than this, where each prime dividing the product initially divides the product at the end. You can't like if a prime divides the product at the start, it's got to divide the product at the end. Okay, why is that true? Because okay, let's say a prime divides two. Let's say a prime divides n, and the prime doesn't divide n. Then the prime is going to divide. It's going to divide a because remember m is ga and n is gb. The prime is going to divide a, not g, so it's going to divide ab. So it's going to be in our product. If the prime divides m and the prime divides n, the prime is going to divide g, and so still be in our product. Yeah, so if a prime divides one term, yeah, so if you look at the set of primes dividing the numbers at the start, that's the same as the set of primes dividing the numbers at the end. Okay, the next thing we need to show is that eventually we have to pick numbers which are co-prime. Because that's the only way you're going to get ones. You're not going to get ones by picking numbers which aren't co-prime. Unless they're equal, of course, because then you have a equals b equals 1. So we need to show that either we're going to have co-prime numbers, which give us 1 as the GCD, or equal numbers, which give us 1 as the LCM over the GCD. Okay, yeah, I think this is, at least in my opinion, this is a bit harder than Problem 1 usually is. Like, if you compare this to, say, I mean, last year, Problem 1 was definitely easier than this. In 2024, Problem 1 was easier than this. Unless I'm missing something quite obvious here. And 2023, of course, that was also a number theory problem, and it was okay. I think my camera is blank. Yeah. So yeah, in my opinion, this is on the harder side of problem ones. Okay. Okay, so I think that if we get part A, we've got part B. Because if we show that we're going to have the number m and the rest ones, then that implies that every prime dividing product at the start divides the product at the end. And so every prime dividing the product at the start is going to have to divide m. And then we can look at the exponent of the Yeah, because the oh, I think yeah, this is good. So the okay, if a prime divides m and the prime doesn't divide n, then the VP of the periodic valuation of the product doesn't change because the VP of A is going to be equal to the VP of n. Yeah, so then it's not going to change. But if the prime divides m and the prime divides n, then the VP of G is going to be the minimum of the VP of M and N. So I think my thing is kind of okay. Uh, yeah, fine. Yeah, okay. So VP of M. Okay. Um, okay, so let's look at what observations we made. So what do we know? So observations. Okay, so if prime divides a number at the start, then it divides the products. Then it divides the, let's say, P of A1, A2, AK, then it always divides that product. Like always. Okay. And furthermore, the periodic valuation of the product is weakly decreasing. Okay. Okay, can I say anything stronger about it? Okay, so if the prime divides m and the prime divides n, then the prime is going to divide both of the next terms. Okay, so we're gonna have let's say that the VP of m is greater than or equal to the VP of n. We have the VP of G is equal to the VP of n, and the VP of A is equal to the VP of M minus the VP of G, which is the VP of M minus the VP of N, and the VP of B is going to be 0. Okay, so the periodic valuation of the prime is constant here. Huh, okay. Okay, yeah. Uh, yeah, in my opinion, not the easiest problem of all time. Okay, okay. Uh, okay, so, oh, I don't agree with this. The VP of the products is the same. I don't agree because In our example, when we had 6 and 4, we went to 2 and 6. So our V2 decreased. Yes, I've made some sort of mistake there. Okay, so this one is G and this one's AB. So the VP of G, okay, let's say this one's M and this one's N. Okay, the VP of G is equal to the VP of M, which is 2, is 1, and the VP of AB, VP of A is equal to the VP of is equal to 0 because M is a small one, and the VP of B is equal to the VP of N minus the VP of G, which is equal to the VP of N minus the VP of M, which is equal to 2 minus 1, which is 1. Okay, so the periodic, okay, so if a prime divides both of them, and the periodic valuation of one of them is more than the other, then the periodic valuation of the product is going to decrease. Okay, okay. So let's say, okay, so if a prime divides both of them, let's say the two VPs are equal. Let's say VPM equals VPN. Then the VP of G is going to be the VP of N, and the VP of AB is going to be 0. Okay, yeah, so the VP, so given a prime that divides the product at the start, the p-adic valuation of the product is strictly decreasing. It decreases every single time, except, okay, it decreases every single time if the prime divides both numbers Confucius picks. So, okay, so let's say the prime divides 1 and doesn't divide it. Let's say P divides N and not N. Then the VP of G is going to be 0, and the VP of AB is going to be the VP of N. Yeah, okay. So in this case, say we have like, I don't know, 4 and 3. Okay, let's do like let's do 6 and 3 because the GCD is not 1, but if we're considering the prime 2, prime divides 6 and not 3. So our GCD is going to be 3, and AB is going to be 2 times 1, so 2. Yeah, so the periodic valuation of the product didn't change. Okay. Okay, so okay, I think we have something. So if a prime divides one term and no other term, okay, what if we had one term that is divisible by like 2 to the 100 and every other term is odd, then what happens? Because then we're in this case and the periodic valuation shouldn't change. So let's look at that. So let's say we have 2 to the 100 and then a bunch of odd numbers. What happens? Okay, well, if I pick 2 to the 100 k and some odd number, um let's say like mk, where m is odd and k is odd, and m and k co-prime. Okay, what are we gonna have? We're gonna have k and then m 2 to the 100. Right, yeah. So if you have, okay, so yeah. So our answer was not correct. Our answer is not going to be the product of all the primes dividing it, because if you have some large prime dividing one of the terms and not the others, then the periodic valuation of the product isn't going to decrease. Okay. Okay. Okay, so let's try an example like that. Let's try an example like 8, 3, 9, 50. Let's see what happens. So if we pick 3 and 9, we're going to have 8, the GCD is 3, and A is 1, B is 3, so we're going to get 3, 3, 15. If we pick 3 and 3, we're going to get 3 and 1, 15. If we pick, oh yeah, if you pick 1 and something, you're also going to get 1 and something again, so that doesn't change anything. So if we pick 3 and 15, our GCD is going to be 3, and we're going to have A is 1, B is 5, so we get 5. Okay, and then, okay, so I think eventually, okay, I think the main thing is eventually we're going to be in a position where we have to pick co-prime numbers. Why is that? Um, oh, okay, I think I see why. Because, okay, so if a prime divides n, and a prime divides n, then the prime is going to divide the GCD. Oh, okay, no, never mind. Okay, so we have to show that at some point, okay, given a prime dividing some term of the sequence, after some number of moves, that prime is going to only be able to divide one term in the sequence. Okay, so I think the answer might be this. So it might be that m is equal to the product of the smallest power of each prime dividing the product of the sum, if that makes sense. So if you look at, if you have A1, A2, AK, you find the maximal power of 2, sorry, the minimal power of 2, which divides a term. And then you find the minimal power of 3 that divides a term. Oh no, okay, what do I mean by this? Like, okay, so an example like 6, 4, whatever, like 10, 15. I think the reason we had the V2 as 1 at the end is because the V2 of these two is 1, and the V2 of this one is 2. So the smaller one is 1. So we end up with 1 at the end. But here, it's 3. And there's no other even number. If we had, say, 6, we'd probably get the V2 being 1 at the end. Because if you do the operation with 6 and 8, the GCD is going to be 2. And A and B, so we're going to have A is 3, B is 4. And we're going to get 12. And then if you do it with 2 and 12, we're going to get 2 and 6. If you do it with 2 and 6, we're going to get 2 and 3. Yeah. So, yeah, so the periodic valuation of the product at the end is going to be the periodic valuation of the of the number which has the smallest, okay, of the number which p divides, and so that the exponent of p dividing that number is min, if that makes sense. So of all the numbers that p divides, the number which has the smallest power of p dividing it, that's going to be your exponent. And why is that true? Well, if you look at that number, say, I don't know, p to the alpha times n, if you pair it with a number, if you do the operation on a number that has a p-adic valuation equal to it, your resultant thing is going to be p to the alpha times some stuff, and then something else which p doesn't divide. And if you do it with a number which has a higher p-adic valuation, p to the beta, where beta is bigger than alpha, well, g is going to be p to the alpha times some stuff. And okay, is this not true? Yeah, I'm not finding this problem easy at all. Yeah. So, okay. Um, yeah. I feel like we were making more progress on problem one. So, yeah, I think, like, yeah, this is by no means an easy IMO day. Like, this is definitely not an easy IMO day. Okay, okay, so let's go to problem one. So, what were we thinking? So we were thinking that if you have a prime that divides some term, we look at all terms so that that prime divides those. And we look at the set of terms that the prime divides, and we take the number with the smallest VP, and that's the VP of the product at the end. That's what we think is true at the moment. Is it true though? Because we did an example, p to the alpha m, p to the beta n, and well, you're gonna get, if alpha is less than beta, you're gonna get alpha times some stuff, and in the other thing, well, you're gonna have the VP of A being 0, the VP of B being beta minus alpha. So you're gonna have p to the beta minus alpha times some stuff. Well, if beta minus alpha is less than alpha, then like, yeah, okay, so what if we have 16, 12, 5, and 15? Then what happens? What's our V2 at the end? If you pick 16 and 12, G is going to be 4. We're going to have 4 and 3, so the product of that is going to be 12. And we're going to have 5, 15. If we now pick 4 and 12, well, GC is going to be 4. I'm going to have 1, 3, so we're going to have 4, 3, 5, 15. Okay, so our V2 is 4, which is exactly what we said it would be. Oh no, I picked a bad example. Okay, let's do okay, we need the number to have V2 3 and V2 2. So let's pick some odd multiple of 8. Like, oh, let's do 8 times 5, like 40. Let's do 40 and then 12. 5, 15. Okay, let's see what happens here. So 40 and 12. Well, G is going to be 4, and we have 10, 3. So we're going to have 4, 30, 5, 15. If we pick 5 and 15, if we pick 15 and 30, we're going to have 4, 5. The GCD is 15, and AB is 1 times 2, so 2. And if we pick 2 and 4, we're going to have 2. A is 1, B is 2, 2, 2, 5, 15. And then if we pick 2, 2, we're going to have 1, 2, 5, 15. Okay, okay. Yeah, so I think, yeah, this is really, it's really unusual. Yeah, I think there's a new theme of this sort of number theory problems coming in Olympiads, where you have, when it's number theory, but it's more about, there's like a combinatorial flavor to the problem. And I think that's what we have in problem 1, IMO 2026. So, okay. Because I feel like the number of terms which are prime divides should decrease. It should decrease. Okay. And why should it decrease? Well, okay, so if a prime divides 2 terms, m and n, I mean, we've been over this, but let's just do it again. If a prime divides m and n, then the prime is going to divide g, and if the VPs of m and n are different, the prime is going to divide ab. Okay. So let's say VP of m bigger than equal to VP of n. So the VP of G is the VP of n, and the VP of AB is the VP of A plus the VP of B, which is the VP of M minus the VP of N plus, well, 0. So it's going to be the VP of M minus the VP of N. So among the terms which he divides, the VP of the product just went down. And before we had VPM, VPN, and now as our VPs, we have VP of M minus VP of N and VP of N. So the VPs, if we look at the set of VPs of the terms, then each move where we pick 2 of them, 1 term's gonna go down. Fine, okay. So 1 term's gonna go down whenever. Okay, so let's say we have a set of numbers. P divides all the numbers. and we have another set, which is the VP region. So we have like A1, A2, like some AL, and then we have VP A1, VP A2, like VP AL. We pick two of these numbers, and okay, so the the VP of one of these is going to go down. Yeah. So then what we have is eventually, some one of the VPs is going to hit zero. Because if okay, so either we're gonna okay, so we're assuming VP of n and VP of n are both at least one. So when we do a move, we decrease the VP we decrease the VP. Like if you look at this set, we decrease the number by at least one. So eventually we're gonna have to like all of them are gonna have to hit zero at some point. All but one of them are gonna have to hit zero. Because if you only have one number left, you have no number to pair it with. And of course, if you do a number from the set with a number outside the set, the VP doesn't change. Okay, so if you look at the set, which is so if our numbers on the board are A1, A2, A2026, and we look at the numbers VP A1, VP A2, VP A2026, if you do a move with a number that P divides and a number that P doesn't divide, then these numbers don't change. The second set of numbers don't change. If we do a move with a number that, if we do a move with two numbers that P doesn't divide either of the numbers, then these numbers stay the same as well. But if we do a move where P divides both of the numbers, then one number in here is going to go down. And so eventually we're going to have all of them be zero and all of them be one. Which means we're going to end up with P only dividing one number on the blackboard. And so we're going to be forced to pick co-prime terms because given a prime after a finite number of moves, after some finite number of moves, that prime is only going to divide one number on the blackboard. And so after some finite number of moves, for every prime that divided the product at the start, each of those primes only divides one number on the blackboard. And so when you take the GCD of any two of them, they're not going to have any primes in common, and you're going to be forced to write down ones. So eventually, we've shown, okay, so we have some numbers on the board, A2026. After some finite number of moves, we're going to end up with a new set of 2026 numbers, so that between them, there's no prime that divides two times. Which means that when we take the GCD of two of them, we're going to get ones. We're going to get one and some other number. That's co-prime with everything. And so once we get a set of numbers like this is going to go to M and then a bunch of ones, which is what. So we've done part A. Nice. We've done part A. Okay. Now we need to show that regardless of what Confucius picks, regardless of what he picks, the number we have at the end is not going to change. Okay. So essentially what we need to show is that once once we have a prime and we condense it so that the prime only divides one number on the board, the p-adic valuation of that number isn't affected by Confucius's moves. Okay, so I think the operation we have is we've reduced it to a different operation. So we have some numbers like VPA1, VPA2, VPA 2026 or K or whatever. And on a move, we can either keep the numbers the same, so let's not consider those moves. But on any other move, we can we can take two numbers, one larger than the other, or equal to each other, and we replace them with the smaller number and their positive difference. Okay, so we take two numbers and we replace them with the smaller of the two numbers and their non-negative difference, rather. Okay, and we need to show that by doing this operation, the number we get at the end is fixed from the start. Okay, so if we have, say, 3, 2, 1, 1, this is what we had in some example we did somewhere. Like, yeah, in our 40, 12, 5, 15, the V2s were 3, 2, 1, 1. Okay, and then we picked 3, 2, and we ended up with 2, 1, 1, 1. That is what we did. Just checking. Oh no, we had zeros. We had not 1, 1. These were 0, 0. Fine. And we had, is that what we ended up with? We had 4, 30, 15. So we had 2, 1, 0, 0. Okay. And then we pick this. We pick. I mean, if you pick something in 0, that doesn't really do anything. Yeah, it doesn't do anything. So if we pick now 2, 1, we have 1, 0, 0, 0. Okay. No, wait. 2, 1. Non-negative difference and the small. So we have 1, 1, 0, 0. And then we have the smaller one and the non-negative difference, so we have 1, 0, 0, 0. Okay, right. So this is a pure common. There's no number theory in this now. Like part B is a pure combinatorics problem. So you have k numbers written on a blackboard, and your operation is you take two of them, you write down their non-negative difference and the small one, and now we need to prove that the number we get at the end is not uniquely determined, but is determined by the numbers at the start and not by which numbers you pick. Okay. So in problems like this, we need some sort of variant. Yeah, we need some sort of variant. And we need to show that, yeah, we need to show something like variance. Okay. Okay, let's just play around with this and see if we can do something. So we have, I don't know, 6, 4, 3, 2, and let's do the operation. So 6, 4, we get 4, 2, 3, 2. Okay. If we pick 3, 2, we have 4, 2, 1, 2. If we pick 4, 2, we get 2, 2, 1, 2. If we pick 2, 2, we get 2, 0, 1, 2. If we pick 2, 2, we get 2, 0, 0, 1. If we pick 2, 1, we get 1, 1, 0, 0. And if we pick 1, 1, we get 1, 0, 0, 0. Okay, so at the start, our conjecture was you get 1, regardless. Our conjecture was, if you remember, that the exponent of p dividing the product at the end is going to be 1. And that's what we're seeing here. And our counterexample to that was, okay, what if you have a really large power of a prime dividing some term and not dividing any other term. Yeah, I think that's sort of a special case. I think that, yeah, I mean, okay, if you do this, the sum of the numbers is going to go down. Okay, yeah, I think we're done. So, unless you have a really big power, okay, so unless you have n and then a bunch of zeros, in this case, you're already done, and you have n with a bunch of zeros. But if you have at least two non-negative numbers, say, if you have at least two non-negative numbers, if you do the operation with a number and zero, that doesn't change the numbers. And if you do the operation on two non-negative numbers, you're decreasing the sum. You're decreasing the sum, and you'd only be adding a zero. Yeah, so a problem is, okay, so we want to argue that you decrease the sum and you keep decreasing the sum, and eventually the sum is, eventually we get a number and a bunch of zeros, and that number has to be one. But we don't know the number has to be one because you could, by some magic, you might end up with, before you get to one, you might end up with some number and then some zeros. So we want to make sure that doesn't happen. Okay, if we have like, let's look at two numbers, like 6, 4, and then a bunch of zeros. Okay, so we can go to 4, 2 with a bunch of zeros. And from 4, 2, we can go to 2, 2 with a bunch of zeros. And then this goes to 2, 0 with, okay, so you could actually end up with 2. Ah, I see, okay. Okay, so if a number, okay, if a number divides all of the terms at the start, all the non-zeros, actually no, just all of the terms at the start, when you apply the operation, it's still going to divide the end number. So the number you get at the end is the GCD of all the numbers. Oh, yeah, because you're basically doing you're basically doing the Euclidean algorithm. Yeah, you're doing the Euclidean algorithm. So by Bezout's lemma, you end up with a GCD of all the numbers. Fine. Okay. So I think, I mean, like, surely in the IMO, yeah, I think this is fine. So in the IMO, you can just say that, okay, we have some numbers, you take a difference, and you write the small one. This is Bezout's lemma. So we end up with the GCD of all of the all of the positive numbers on the board. But we actually, regardless of the moves, and I think this is some sort of extension of Bezout's lemma. Yeah. Yeah, I think this is an extension of Bezout's lemma. So you have some numbers written on the blackboard, and you take the difference, and you write the smaller one, and then you have to end up with a GCD. I think, yeah, I think this is fine. Okay, okay, that's problem one done. Nice. Okay, so we got one problem at least. Now, okay, so we've got about 3 hours for problem two now. Yeah. Yeah. So and yeah, that was quite a long time for problem one. So, okay, so okay, what I'm gonna do, I'm gonna write up question one. Yeah, I think yeah, I think write up is also quite important. And I think the last step at the end with the Zeus lemma is not that rigorous. So I'm gonna write up question one. I'm gonna be thinking about this problem while I'm writing it up. So yeah, I'll just take a page from it. Let's write up question one. So I'll keep this diagram in front of me. I'll be looking at it and I'll be writing this little problem. So IMO 2026. P1. Okay. So what do we do? We said that Um, the main claim is that, well, at some point, given a prime, at some point, the prime divides at most one time. Okay, so claim 1, let's say. Given a prime key, after a finite number of moves, P divides at most one of the 2026 numbers. Okay, proof. Okay. Consider A1, A2, A, they're already 2026, and VP A1, VP A2, VP A2026. This is like the core of like considering these numbers. I think that's the core of the problem. Suppose, okay, ignore terms with VP AI is 0. Consider, say we have like a blog VP A1, VP A2, VP AK left with VP AI greeting to 1 for all I between 1 and K. Yeah. On a move, applying a move to two numbers outside these K does not affect our second list of numbers, the one with VPAI, because you're sending 0 to 0. Applying a move to a number in our K numbers, and P divides almost one of these two, and the VP. Oh, no, I'll say that's claimed since the VP of that number is fixed. Applying move to a number in our K numbers and one outside gives GCD MN, like P doesn't divide GCD MN, and VP LCM MN over GCD MN equals VP LCM MN equals VP of M or VP of N, whichever one is in the like block of K. So again, the list of VPs is unchanged. It is unchanged. Okay, now suppose we apply a move to two numbers in our first K. We end up with, say AI and AJ. We'll log the VP of AI is at least the VP of AJ. the VP of the GCD of AI and AJ is going to be the VP of AJ. The VP of LCM of AI AJ over the GCD of AI AJ is going to be the VP of AI minus the VP of AJ. Yes, because we have LCM is JB, GCD is G, so you get AB, and the VP of B is going to be 0, and the VP of B is going to be 0, and the VP of A is going to be the VP of M over the VP of G, which is the VP of M over the VP of N, which is this thing. This thing, next page. So, it's like, how do we argue rigorously that that means that all the numbers go to 0? Like, I'll say like the smallest number decreases. Yeah. So I'll say like, so after a finite number of moves, after a finite number of moves, the smallest number, the smallest VP must have decreased. Decreased because, actually no, wait, it need not have. I think I'll just say like, it's so like obviously they go to 0, right? Like obviously they all go to 0. Okay, now we claim that after a finite number of moves, a finite number of the third type of moves, we end up with the second list being something like A000. Like this is obviously true, so we need to prove it. I think the thing with Bazoo's lemma isn't that rigorous either, so yeah, I mean, we've solved one problem so far, we need to ensure we're getting, like, we need to get 7 on this problem. Um, oh, okay. And we can argue the sum thing with using the sum. this is again, this is like pure combi. Like if you have like A1, A2, AL, and you keep the smallest one, and you replace two terms with the smaller one and the difference, why do you end up with a term and a bunch of zeros? There's no way we're gonna do a small case of this. Like this is it's just obvious now. Okay, one, like 7, 5. When you pick 7, 1, you get 1, 6, 5. When you pick 5, 1, you get 1, 6. I feel so stupid doing small examples on this thing. If you pick 1, 6, you get 1, 5, 4. Yeah, like the numbers are going down. Um, yeah. Okay, wait. Oh, wait. The sum. Oh yeah, no, I had the argument before. Escape. As long as we are doing moves with two non-zero terms, zero VPs, the sum of the VPs strictly decreases. And if the sum is strictly decreasing, so as long as we have at least two terms, two non-zero terms, eventually one term must hit zero, as you can't keep strictly decreasing the sum of a set of positive integers forever, because it's bounded below by zero. So one of them must hit zero. So we lose a non-zero term. When we have two non-zero terms left, again, the sum strictly decreases. So one of them must hit zero. And we are left with only one non-zero term. Okay, so that's the thing up. Claim 2, this non-zero term is the GCD of all the non-zero VPs, VPAIs or whatever. Proof. So, I mean, like, okay, so this clearly divides the last two non-zero terms. If it's the GCD of them, of these two terms, by Euclidean algorithm, because the Euclidean algorithm only applies to two integers. We're done. It clearly must divide the last non-zero number as the operation preserves divisibility by G. Okay. Okay, so I'm gonna say when you go from k non-zero terms to k minus one non-zero terms, the GCD doesn't change. Why is that? Well, yeah, okay, so if you have G, okay, we're using so if you have GB1, GB2, GBK, and let's say GBK hits the floor first, means that means what? Means that okay, what could have happened? Okay, so like, when we perform a move, we go to like GB1, GB2. Let's say GBK is a small one. We have GBK minus one minus BK, and then GBK. And then you worry, okay, what if there's a number that divides B1, B2 up to BK minus 2, BK and this thing? But if that were true, then that number would have divided BK minus 1 as well, which is a contradiction. Okay, oh yeah, so I think that's fine. So after a move, the GCD of all the terms doesn't change. Yeah, that's sufficient, fine. Okay, so moreover, it preserves the GCD of all the terms because take GB1, GB2, GBK, apply the move to GBK minus 1, GBK, we get GB1, GB2, GBK minus 2, G, let's say this one's bigger, or equal to GBK minus 1 minus BK, and GBK. If the GCD changes, there's some G prime dividing BI for all I between 1 and k minus 2, and I is k, and G prime divides BK minus 1 minus BK, implying G prime divides BK minus 1 as well, contradiction. So if the last non-zero term weren't G, well, okay, the last non-zero term has to be the GCD of all the terms, because everything divides 0, so it has to be the GCD of all non-zero VPAIs, and then on another page, I'll just finish by saying that Yeah, okay, so once we've got this, taking the GCD of what? Okay, so after some finite number of moves, we end up with a a list of numbers where, given a prime, it only divides one of the 2026 numbers, meaning every two numbers, the GCD is 1, and the LCM over the GCD is the product. So we end up and I'll say, and its exponent is known. So we end up with the product of all these numbers. Since we know since the exponent of each prime of this number is known from the original set of 2026 numbers, this number is known. Okay, that's parts A and B solved. This number is known, and all the others are ones. Others are ones because of the GCDs. Yeah, and he has to pick numbers and drink one. Fine. Okay, we're done.